312 topic. I'll be discussing on the chemistry of 5-membered compounds with one or more heteroatoms. Definition of heterocyclic compounds. Heterocyclic compounds are cyclic organic molecules that contain at least one or more heteroatoms. An atom other than carbon, such as nitrogen, oxygen, or sulfur, within the ring structure. These compounds are distinguished from carbocyclic compounds, which consist solely of carbon atoms in the ring. Heterocycles can be classified based on the number and type of heteroatoms, the degree of saturation, and the presence of aromaticity. For instance, pyro, furan, thiophene are examples of 5-membered heterocycles with one heteroatom, nitrogen, oxygen, and sulfur, respectively. Importance of 5-membered heterocycles in chemistry and applications. 5-membered heterocyclic compounds are of paramount importance in both academic research and industrial applications due to their versatility and prevalence in natural and synthetic systems. These compounds are ubiquitous in pharmaceuticals, agrochemicals, and material science. Beyond life sciences, 5-membered heterocycles are critical in material science, particularly in the development of organic semiconductors, dyes, and polymers. Then we move on to the classifications of 5-membered heterocyclic compounds. Heterocycles with one heteroatoms. 5-membered heterocyclic compounds with one heteroatoms are among the most studied heterocycles due to their aromaticity, stability, and wide-ranging applications. These compounds typically contain nitrogen, oxygen, or sulfur as the heteroatoms, and their properties are heavily influenced by the nature of heteroatoms. The three primary examples are pyro, furan, and thiophene. Pyro is a 5-membered aromatic heterocycle containing one nitrogen atom. Is pyro, furan is aromatic, with the oxygen atom contributing one lone pair to the 6-electron system. However, furan is less aromatic than pyro or thiophene due to the higher electronegativity of oxygen, which reduces electron delocalization in the ring. Furan is highly reactive towards electrophilic substitution, but its ring is prone to opening under acidic conditions, limiting instabilities in certain environments. Furan derivatives are found in natural products and are used in the synthesis of pharmaceuticals and polymers, such as polyfuran. Thiophene C4H4S contains one sulfur atom in its 5-membered aromatic ring. Sulfur contributes one lone pair to the aromatic system, making thiophene highly aromatic and more stable than furan. The lower electronegativity of sulfur compared to oxygen enhances the electron density in the ring, making thiophene less reactive towards ring opening reactions. Thiophene undergoes electrophilic substitution primarily at the 2 position and is a key component in organic electronics, such as organic field transistors and organic photovoltaics. Thiophene derivatives are also found in certain drugs and agrochemicals. Heterocycles with 2 heteroatoms. 5-membered heterocycles with 2 heteroatoms exhibit increased structural complexity and diverse chemical properties due to the presence of multiple heteroatoms, typically nitrogen, oxygen, or sulfur. These compounds are widely used in medicinal chemistry and material sciences. Imidazole C3H4N2 is a 5-membered aromatic heterocycle with 2 nitrogen atoms, one which is pyro-like, contributing to the system, and the other pyridine with a lone pair available for coordination and protonation. This dual nature makes imidazole amphoteric, capable of acting as both an acid and base. Imidazole is a critical component in biological molecules such as histidine and histamine, and in pharmaceuticals, including antifungal agents like clotrimazole. Its ability to coordinate with metal ions also makes it valuable in catalysis and material sciences. Pyrazole. Pyrazole C3H4N2 contains two adjacent nitrogen atoms, one of which contributes to the aromatic system, while the other has a lone pair available for protonation. Pyrazole is less basic than imidazole due to the electron withdrawing effect of the second nitrogen atom. It is widely used in pharmaceuticals such as the anti-inflammatory drug and in agrochemicals due to its bioactivity. Pyrazole reactivity includes electrophilic substitution at the 4 position and nucleophilic attack at the nitrogen atoms under specific conditions. We have oxazole, thiazole. Then we move on to the heterocycles with 3 or more heteroatoms. 5-membered heterocycles with 3 or more heteroatoms are less common but have significant application, particularly in medicinal chemistry and click chemistry. These compounds also contain multiple nitrogen atoms, increasing their polarity and reactivity. We have under the three or more heteroatoms, we have triazole, we have tetrazole. Triazole exists, triazole C2H3N3 exists in two isomeric form, 1,2,3-triazole and 1,2,4-triazole. Both are aromatic with 3 nitrogen atoms contributing to the system or providing lone pairs for coordination. 1,2,3-triazole is particularly notable for its synthesis via copper catalyzed azide alkene cycloaddition, a cornerstone of click chemistry. Triazoles are widely used in pharmaceuticals. Example, antifungal drug fluconazole and as ligands in coordination chemistry due to their stability and versatility. We have tetrazole. Tetrazole CH2N4 is a 5-membered heterocycle with 4 nitrogen atoms, making it highly electron deficient and acidic. The tetrazole ring mimics the carboxylic acid group, making it a biosphere in drug design. As seen in the antihypertensive drug losartan, tetrazoles are synthesized via cycloaddition of azide with nitriles and are used in explosives, pharmaceuticals, and coordination chemistry due to their high nitrogen content and stability. Structural and electronic properties of 5-membered heterocyclic compound. Aromatic. One is aromatic in 5-membered heterocycles. Aromaticity is a fundamental property of 5-membered heterocyclic compounds, contributing to their stability and unique chemical behavior. Aromatic compounds possesses a planar cyclic structure with a delocalized electron system that satisfies Hooke's law, requiring 4n plus 2n electrons. 5-membered heterocycles such as pyro, furan, thiophene, and imidazole and triazole typically contain 6 electrons, fulfilling the aromaticity criteria. The heteroatoms, nitrogen, oxygen, or sulfur, play a critical role by contributing lone pairs of p orbitals to the system. Then we have resonance and conjugation. Resonance and conjugation are central to the electronic structure of 5-membered heterocycles, governing their reactivity and stability. Resonance refers to the delocalization of electrons across the ring, resulting in multiple contribution resonance. Structures that stabilize the molecule. In pyro, for example, resonance structure depicts the nitrogen lone pair participating in the system, distributing electron density across the ring. This delocalization enhances the electron-rich nature of pyro, making it highly reactive towards electrophilic aromatic substitution. Influence of heteroatoms on electronic properties. The nature and number of heteroatoms in 5-membered heterocycles profoundly influence their electronic properties, including electron density, basicity, and reactivity. Heteroatoms contribute to the system, modulate electronegativity, and introduce lone pairs that affect the molecule's chemical behavior. We have nitrogen, oxygen, sulfur. Nitrogen. In pyro, the nitrogen atom donates its lone pair to the aromatic system, increasing electron density and making the ring electron-rich. This enhances pyro reactivity towards electrophiles but reduces its basicity as the lone pair is not readily available for protonation. Oxygen. In furan, the oxygen atom's high electronegativity withdraws electron density from the ring, reducing its aromaticity and electron-rich character compared to pyro or thiophene. This makes furan more susceptible to electrophilic attack but also less stable as the oxygen lone pair is tightly held, limiting its contribution to the system. Sulfur. Thiophene sulfur atoms with its larger 3p orbitals provide a more diffuse lone pair, enhancing conjugation and aromaticity. Sulfur's lower electronegativity results in a more electron-rich ring, making thiophene less reactive towards ring opening and more stable under harsh conditions. Synthesis of five-membered heterocyclic compounds. General synthetic strategies. The synthesis of five-membered heterocyclic compounds with one or more heteroatoms is a cornerstone of organic chemistry, driven by their widespread applications in pharmaceuticals, agrochemicals, and material science. General synthetic strategies for these heterocycles involve cyclization reactions, where acyclic precursors are transformed into cyclic structures through the formation of carbon heteroatom or carbon-carbon bonds. These strategies can be broadly categorized into intramolecular cyclization, cycloaddition, and multi-component reaction. Specific synthetic routes for heterocycles. The synthesis of specific five-membered heterocycles varies depending on the heteroatoms and desired substitution pattern. Below as detailed synthetic routes for some representative heterocycles: pyrosynthesis, imidazole synthesis, triazole synthesis. Okay, I'll be talking on the pyrosynthesis. Pyro, a five-membered heterocycle with one nitrogen atom, is commonly synthesized, a versatile and widely used method in this reaction. 1,4-dicarbonyl compound reacts with a primary amine or ammonia under acidic or neutral condition to form the pyro ring. The reaction proceeds through imine formation, followed by cyclization and dehydration. Imidazole synthesis. Imidazole, a heterocycle with two nitrogen atoms, is synthesized through several established methods, being the most prominent. This multi-component reaction involves the condensation of a 1,2-dicarbonyl compound, an aldehyde, and ammonia, also in the presence of an acid catalyst. The reaction proceeds via formation of the diimine intermediate, followed by cyclization to yield the imidazole ring. Then we have modern synthetic approaches. Recent advancements in synthetic methodology have revolutionized the preparation of five-membered heterocycles, emphasizing efficiency, sustainability, and scalability. Then unit 5, we have chemical reactivity and reactions of five-membered heterocyclic compounds. Electrophilic aromatic substitution. Five-membered heterocycles compounds such as pyro, furan, thiophene, and imidazole are electron-rich due to the contribution of heteroatoms, nitrogen, oxygen, or sulfur, to the aromatic system, making them highly reactive toward electrophilic aromatic substitution (EAS). EAS involves the replacement of the ring hydrogen with an electrophile facilitated by the electron-donating nature of the heteroatom. The reactivity order among heterocycles with one heteroatom is typically pyro, furan, thiophene, reflecting differences in electron density and aromaticity. Then we have functionalization of heterocycles. Functionalization of five-membered heterocycles involve introducing or modifying substituents on the ring to tailor their properties for specific application. Beyond EAS and cross-coupling, other functionalization strategies include CH activation, lithization, heteroatoms, and directed reactions. Applications of five-membered heterocyclic compounds. Pharmaceutical and drug discovery. Five-membered heterocyclic compounds are pivotal in pharmaceutical chemistry, constituting a significant portion of approved drugs. due to their structural diversity, bioactivity, and ability to interact with biological targets. Approximately 60% of small molecule drugs approved by the US Food and Drug Administration (FDA) contain at least one heterocyclic motif with five-membered heterocycles like imidazole, triazole, and pyrrole being particularly prevalent. Then we have natural products containing five-membered heterocycles. Pyrrole. Pyrrole is a key component in porphyrins such as heme in hemoglobin and chlorophyll in plants, where the pyrrole units form a tetrapyrrole macrocycle that coordinates metal ions. Indole is used for pyrrole derivative is found in a tyrotrophan and alkaloid like serotonin and indole-3 acetic acid, a plant hormone. Imidazole is present in histidine, a critical amino acid in enzyme active site, and in histamine, a neurotransmitter. And we also have furanthiazole. Analytical categorization of five-membered heterocyclic compounds. Spectroscopy techniques.
2 minutes to go.
Spectroscopy techniques are essential for categorizing the structure, electronic properties, and purity of five-membered heterocyclic compounds such as pyrrole, furan, thiopine, imidazole, and triazole. This method provides detailed information about the molecular framework, functional groups, and electronic transition. In conclusion, the seminar on the chemistry of five-membered heterocyclic compounds with one or more heteroatoms has provided a comprehensive overview of their significance in organic chemistry and related fields. These heterocycles, including pyrrole, furan, thiopine, and imidazole, triazole, and tetrazole, are defined by their cyclic structures containing heteroatoms such as nitrogen, oxygen, or sulfur, which impart unique electronic and structural properties. Their classification based on the number and type of heteroatom highlights their diversity, with each compound exhibiting distinct aromaticity, resonance, and reactivity profiles. Thank you.
Thank you very much. Thank you very much. That was a wonderful presentation and in-depth presentation of the chemistry of five-member compounds. But I expected you to give us their structures on the board, so especially when you're describing the synthesis. But you just look as if you just rushed the synthesis. What happened? Please, it's chemistry. This is chemistry. Even though it's pharmaceutical chemistry, medicinal chemistry, it's still chemistry. You cannot talk of chemistry without talking about the what? The structures. Yes, you described it, but I was expecting to see what you were saying on the board, draw them, you know, when you're talking about electrophilic attack, I was expecting you to, and how nitrogen will draw electron towards itself, and I was expecting that, to especially resonance, how the movement of the electrons, I was expecting that, but I didn't see it. So how do you go about it? All right, thank you very much. Please let's give another. All right, thank you very much. Thank you very much.
Yes, sir.